For an acid, you will always use HA, dissociates into H plus, and the base, the conjugate base, A minus.
We haven't gone over the bases yet.
We haven't done as many, so we haven't really gone over the bases. Madeline, right?
Yeah.
Madeline. What are your initial concentrations? That's the concentration of what? HA. That's the initial concentration of HA. Okay? I'll just leave the molar off. But 0.122 is the initial concentration of HA. What is the initial concentration of H plus? 0. Now I'll leave you to it.
So once we do this, how do you check if it's within the 5%? You divide.
So did you drop that?
Yeah.
And then you did the square root and you found this.
Mm-hmm.
Okay. Then you look at this 1.22. Okay. You take this divided by 1.22 times 100. or 0.122. I'm sorry.
So if it's more than 5%, we have to do the quadratic. It's more than 5%.
If it's over 5%, then the assumption would be that you would need to do the quadratic. Okay, so hopefully you guys are getting at least this far, right? And then we're going to make the assumption that we're going to drop the x, okay, in that case, and then our x is 0.0083, and then a lot of you did this to find it 6.8%, right? So that's more, so it's not okay to make that approximation, so you got to go back and do the quadratic.
Can we just work it out anyway?
What's that?
Can we just work it out and
Yeah, of course.
it's okay?
Yeah, that would be the most, you would know it's right that way. So you wouldn't have to, you could just do the quadratic formula if you wanted. Initially, okay? Okay, and then you get back, is this what you guys are getting? From the quadratic? .0086? Oh, 806, yeah. Yeah, yeah. Which, and if you see, it's not actually that much difference than what you really initially got, but to be more accurate, we would want to use the quadratic there. Okay, so if my x is 0.0081, then that's the concentration of H+. Okay? So I went through that process of doing the Rice table and everything so that I could find what x is, because x is the concentration of H+. And that's going to tell me my pH by doing what? The negative log of 8.1 times 10 to the negative 3. Okay, so whatever that is, that's going to be my pH. So what is it? 2.094. Okay. So that's our pH. Okay, so that's a very common type of question. What is the pH of the concentration of this acid? Okay. Now, you would probably notice if you put in, what's the pH of, let's just go back here. So for 0.081, it was 2.09. For, what is the pH of that?
2.08.
So you can see, if you didn't do the quadratic equation, you're still going to get an answer probably almost exactly the same. Okay. But the assumption was made that because it's over 5%, we would do the quadratic equation. All right. All right. And I would say most of the time you're just going to end up not needing to, if it's that close. Okay. All right. Percent ionization. Percent ionization is simply talking about the percent of hydrogen that is dissociated from the original concentration. Okay, how much hydrogen has come off of that initial concentration of that acid? So to find the percent ionization, you're going to look at the ionized acid concentration, the H plus ion concentration, at equilibrium, just like we just found that concentration, versus the initial concentration of the acid. Okay, so if I know the initial concentration of the acid, and I know the how much hydrogen has come off, maybe through a pH meter. Maybe I would measure the concentration by pH. This is what you guys are going to do in the lab. You measure the pH. So that's going to tell you how much free hydrogen is in solution. And then you're going to describe the percent ionization because you'll know the initial concentration of that. So you'll take the ionized concentration of hydrogen over the initial concentration times 100, and it will tell you the percent ionization. Okay, so here we have the H plus over the initial concentration times 100 is our percent ionization. Now, this is an interesting fact about percent ionization. Look at the initial concentration here at right after concentration 0. So the lower the initial concentration, the higher the percent ionization. Initially, that percent ionization is almost 100%. But as I get something that's more and more concentrated, look at that ionization, percent ionization. It decreases. Okay? The percent ionization will decrease. So if you have something that is very, very, very dilute, its percent concentration or its percent ionization will be very high. It's going to have a very high percent ionization. But as you make it more and more concentrated, okay, more and more concentrated, that percent ionization decreases, okay, very quickly. That's also what you're going to do in the lab. You're going to take a more concentrated solution and a less concentrated solution, and you're going to verify the percent ionization that it follows this trend, okay, for a weak acid. A strong acid obviously would be 100% all the time, 100% ionization all the time. Okay, bases. So bases aren't really that much different than acids. The only thing you need to remember for a base is that you need to include the water in the equation. Okay. So ammonia is a base, and it will react with water to form ammonium and hydroxide. So when you're working with a base, this is what you need as one of your products, hydroxide. That's why we have water in the equation, so that we can show that hydroxide forming, because water will donate a hydrogen to the base and produce hydroxide in solution. Okay, so if you have a ammonia water solution, this is what it's doing. It's pulling hydrogens off of that water and creating hydroxide in solution, making it basic. Okay, so this is an equilibrium base equation, and therefore we have a Kb, and the Kb is equal to the products over the reactants, ammonia and hydroxide over ammonia, okay, for this particular case. Okay, that's your Kb ionization constant. Okay, so we're going to solve these exactly the same as we would solve for H+. Okay, we're just going to solve for OH minus instead. Okay, so my X here would be for OH minus instead of for H+. And then I could find from that, I could find a POH, and then I could find a pH, or I could find the I could find a POH, or I could find H+ directly from the OH minus. Okay, so either way, I can find the. But the questions usually ask, what is the pH? What is the pH? What is the pH? What is the pH? So in this case, if I was looking for the pH, X would equal my OH minus. I would find the POH from X and then the pH, or I would go from OH minus to H+, and then I would find the pH from the H+. Okay, but either way, it doesn't matter which way you go. Here are some KBs for different bases: ethylamine, methylamine, ammonia. Ammonia and acetic acid are very common questions, I should say. Okay, those are very common. That's a very common acid that you'll get a question with, and and ammonia is a very common base. And if you look at their Kb, the Kb of ammonia is 1.8 times 10 to the negative 5. The Ka of acetic acid is 1.8 times 10 to the negative 5 as well. Okay, so they both kind of have that same. And that's a very common one that you'll see and use a lot. So I think you'll start to recognize that. Okay. Come on. Okay, so what you can see here is that if I react an acid with a base, okay, I have a Ka for the acid, I have a Kb for the base, and the overall result of that, once all the spectator ions cancel and everything on each side cancels, is I'm left with water, produces H+ and OH minus, okay, which is my Kw. And remember I told you that if you're given a Kb, you can find a Ka because the Ka times the Kb equals the Kw. And that's the case here. Ka times the Kb equals your Kw. So if I need to find a Ka, I simply put my Kw on top divided by my Kb, and it'll give me the Ka. Or if I need to find the Kb, I put my Kw on top divided by my Ka, and I'll find my Kb. Okay. Now we have acids that have more than one hydrogen on them at times. Okay, and we say these are polyprotic acids. Diprotic and triprotic, okay? And each hydrogen that would be associated with these has its very own Ka. So here, carbonic acid, we see dissociates one hydrogen into hydrogen carbonate, or bicarbonate, okay? The bicarbonate ion. There's a Ka for that hydrogen coming off. But then there is also a second step right? Whereby carbonate can dissociate its hydrogen, and you're left with carbonate. And that has a Ka as well. There's a Ka for the first hydrogen coming off. There's a Ka for the second hydrogen coming off. This one will always be lower than this one because this one is strong. This is a stronger step. The first step is always the stronger step. The second one is always weaker than it. Okay, but each one is a equilibrium step that will occur. So if I dissolve H2CO3 in solution, okay, then you're going to get one hydrogen that comes off in equilibrium, and then you're going to get a second hydrogen that comes off in equilibrium, and all these steps will all be occurring in that one solution. Okay. And here for those diprotic acids, we can see different Kas for the different steps. So phosphoric acid, okay, phosphoric acid has 3 hydrogens, and each one will come off in a weak acid dissociation step. The first one you can see is 7.5 times 10 to the negative 3, okay. This one is 6.2 times 10 to the negative 8. You can't see it very well. This one is 4.8 times 10 to the negative 13. Okay? So you can see each hydrogen has a less and a less extent of coming off due to the fact that these bases that are produced start to become stronger and stronger as you're going down this way. Okay? So H3PO4 is an acid. It's going to donate a hydrogen. Dihydrogen phosphate is going to donate a hydrogen in a weaker step. Okay, and then this guy's pretty weak. In fact, you would probably consider that to be a base. If you dissolved hydrogen phosphate in solution, it would end up being a basic solution, not an acidic solution. Okay. Well, how could I dissolve hydrogen phosphate in solution? Well, you put a sodium on it. Sodium HPO4 Na2HPO4. Okay. Sodium hydrogen phosphate. I dissolve that in solution, and I would end up with HPO4 2 minus, and it would react with water to produce H2PO4 minus plus OH minus in solution. Okay, so it's a stronger base than it is an acid because its acid ionization constant is very low. Okay, so you can see here for HPO4 2 minus, its acid ionization constant is 4.8 times 10 negative 13. But right here, as a base, HPO4 2 minus is 1.6 times 10 to the negative 7. Okay, so it has a stronger acid or base ionization than it does acid ionization. Okay. Okay. So this is going to help answer your questions earlier, Patrick, about why acids and bases are stronger, weaker, and so forth. Okay. Told you we get to it. So the stronger the bond, the weaker the acid. Right? It makes sense. If that hydrogen doesn't want to come off, it's not going to. Okay? But if I have a weak bond between the hydrogen and the metal, usually, or in a lot of cases a non-metal, okay? Well, non-metals mostly, okay? Then the weaker that bond becomes, the easier the hydrogen comes off, the more acidic your solution becomes, okay? So we talk about how HCl, HBr, HI, they're all strong acids, okay? And they dissociate 100%. And HF is a weak acid, Okay, we say it's a weak acid. So why is that? Why is it that these guys are stronger than HF? And it has to do with the molecular structure of them. Okay? So, whoops. As you go down that column, the acidity increases. So, even though HCl and HI are both strong acids, we do consider HI to be a stronger acid because the hydrogen has a harder time holding on to HI than it does the HCl. Okay? And the reason for that is size. It's the size. How many energy levels are around fluorine? 2. It's in the second energy level, right? There's 2 energy levels. How many are around chlorine? 3. Bromine? Iodide? 5. Right? So I have a hydrogen that is bonding to the valence shell of all these, and the protons are in the middle, right? And they have to hold on to all these electrons. So if I bond a hydrogen to a fluorine, then the electrons between the hydrogen and the fluorine are they're closer to the nucleus, and fluorine will have a stronger hold onto those. Okay? But as I get up into iodide with 5 valence shells, or not 5 valence shells, but 5 energy levels, okay, then because of its size, it doesn't hold on to that hydrogen as well. But it's still it's an electronegative element, so it's pulling electrons away, but that hydrogen has a hard time holding on to that molecule, so it falls off more easily. And so that's why HI is a stronger acid than HF. So here we see the strength of that bond between the hydrogen and fluorine, between hydrogen and chlorine, between hydrogen and bromine, and hydrogen and iodine. Okay? So here, this one has the strongest bond, therefore it's the weakest acid, because it holds on to it more tightly than the others. Okay, now, oxy acids. So we have oxygenated acids from polyatomic ions. And the strength of these acids are dependent on the number of oxygens versus the number of hydrogens associated with them. So it's a ratio between the hydrogens and the oxygens in the molecule. Okay? Because that hydrogen has to bond to the oxygen and has to hold on. Okay? Okay, so here we see a few examples. So here we have carbonic acid. Okay? Carbonic acid is a weak acid, and it has 3 oxygens and 2 hydrogens. Okay? So that oxygen to hydrogen ratio isn't that much different. Okay? So, and carbon is not a very electronegative center. Okay? So it doesn't pull electrons away as strongly. If I had something more electronegative in the center here, the more electronegative it is, the stronger it has a pull on those the electrons of the hydrogens here, and it pulls those electrons away, and the hydrogen would fall off more easily. Okay, so oxygen is already electronegative. If carbon was electronegative as well, then this hydrogen would come off more easily because of that pull. Okay, but carbon is not very electronegative. Okay, and we have these 3 oxygens versus these 2 hydrogens, and so this becomes more of a weak acid. Okay. Now, here we have nitrous acid. Nitrous acid has a 2-to-1 oxygen ratio, oxygen to hydrogen ratio. Okay, nitrogen is pretty electronegative. Okay, but I have 2 oxygens, only 2 oxygens, and 1 nitrogen pulling on that hydrogen. Okay, and it does create a weak acid there. But look what happens when I have 3 oxygens, a nitrogen, pulling on this hydrogen. Now it becomes a strong acid. Okay, so this wasn't enough to make it a strong acid, but then I move here from nitrous to nitric acid. Now nitric acid, the ratio of oxygen to hydrogen has changed. Okay, I have all these oxygens and a nitrogen pulling electrons here away from hydrogen, and that hydrogen is going to fall off. Okay, because the electronegativity is so great that it just can't hold on to it. So it becomes a strong acid. So nitric acid is a strong acid. 3 oxygens, 1 hydrogen, that's going to be a strong acid. Okay? 2 oxygens, 1 hydrogen, not as strong. This is a weak acid. Weak acid, we have 3 and 2 hydrogens and a carbon, which is not electronegative. Okay? Okay, so we have 3 hydrogens and 3 oxygens, right? So this is a weak acid. Phosphorus acid, weak acid. Phosphoric acid is also a weak acid. 4 oxygens, 3 hydrogens. The ratio of oxygens to hydrogens isn't great enough to make it a strong acid. Okay, if I had 4 oxygens and 1 hydrogen, that would become a strong acid. Okay, like HClO4. Perchloric acid. Perchloric acid is a strong acid. 4 oxygens, 1 hydrogen. That's a strong acid. Okay, but phosphoric acid, 4 oxygens, 3 hydrogens. It's not. Okay, it's not as strong. Even though I have a lot of oxygen character here, I'm pulling electrons from 3 things instead of just 1. If I only had 1 hydrogen here, those electrons would be pulled all the way this way from that 1. But I have to pull here. I have to pull from all 3 of these. Okay, and it will create it'll cause it to come off, just not in a strong 100% ionization step. Okay. Don't get me wrong, these are still pulling pretty hard, and these hydrogens are falling off. It's just that they fall off and come back on, fall off, come back on in equilibrium steps. Okay? So they create equilibriums there. Okay, so here we have some acid strengths. Okay? So chlorine is more electronegative than bromine. That's why this one, you would have an increase in the acid strength due to the electronegativity of the central element as well. Okay? So HClO3 is stronger than HBrO3 because of the electronegativity. So chlorine, right, we would consider to be more electronegative than bromine. And therefore, it has a stronger pull. We have 3 oxygens, 1 chlorine pulling on this hydrogen. Okay, this chlorine is more electronegative than this bromine. So overall, the electronegativity of this whole group here is lower than this whole group here. That's pulling on that hydrogen. Okay. Now that's different than when the hydrogen is bonded directly to the chlorine or the hydrogen is bonded directly to the bromine. Because in that case, without all those extra oxygens, okay, then it becomes a matter of the size, how big it is, and how strong that bond becomes between the hydrogen and the chlorine directly, or the hydrogen and the bromine directly. Okay. So, chloric, bromic, and iodic acid, we would have a decrease in the acid strength between all 3 of those. Okay.
So if it's not an oxo acid, the acidity increase is going down because they're getting bigger.
That's right.
If it is an oxo acid, since they're all attached to the oxygen, then acidity increases.
Then they increase. Then they just add their electronegativity to the electronegativities of the oxygens, which are already highly electronegative, and that just adds to the pull against that hydrogen.
All right. So I mean, we don't really need to remember exactly what's more electronegative than the other ones. It's kind of just the general rule is going up. So if you give us, I mean, like I don't even know, HiO3 versus HClO3, then we would say HCl is more because it's more electronegative because it's higher, basically. In oxo acids.
It's the one closest to fluorine. It's the more electronegative.
Yes, that's true. So the thing that's more electronegative would be closer to fluorine, okay? And if the hydrogen is bonded directly to the halogen, then the acidity strength increases going down the group, okay, by size. But if the central element is surrounded by oxygens, which are bonded to a hydrogen, then it's like 1, 2, 3, 4 things all pulling against this hydrogens. And then the electronegativity is increased in the opposite way. Iodine, bromine, chlorine.
So with no oxygens, acidity increases as
Downward.
you go down. And then once you add oxygens into it, acidity will increase as you increase.
That's right.
Is that only for the ones in the same group though?
I'm sorry.
Is that only for the same one for the?
That's for the halogens, okay? And that's what we'll focus on mostly. I mean, as far as groups go, okay? Because once we get into sulfur or phosphorus and those kind of things, we're not really looking at that kind of consideration, a whole group. But the halogens, we do look at that. We try to understand because those are common acid molecules, the halogens, okay? Oops. Okay, so acid strength increases as the oxidation number of the central of that central element increases as well. Okay, so this is for chlorine, and once again, you can kind of look at this as the oxygen to hydrogen ratio because that ratio is going to change the oxidation number of the central element. Okay. The more oxygens I have will change. So what is the oxidation number of the chlorine in this molecule right here? Of chlorine right here. What's the oxidation number? Oh. The oxidation number. Okay, so what is the oxidation number of an oxygen? -2. Okay. What is the oxidation number of a hydrogen?
+1.
+1. So that means this has to be +1 because it has to balance the -2. Okay. So that's +1. And what's the oxidation number of this chlorine right here? Well, this goes to -4 for the 2 oxygens. It's -2, but there's 2 of them, so that's a -4. This is +1, so this becomes +3. Okay. -6 +1 +5. -8 +1 +7. Okay? So they're saying as the oxidation number increases, but what does that mean? It means you're getting more oxygens. That's all that really means. So the oxygen to hydrogen ratio is getting greater. Okay? So that's what that's talking about. So as I increase that oxidation number, I have more oxygens here, which makes this this whole thing more electronegative and gives a greater pull on that hydrogen. And it's pulling those electrons with a stronger attraction away from that hydrogen, and it's going to fall off into H+. Okay? So this is a strong acid. Chloric acid. I can't remember if chloric acid is strong. I think so. This is strong, and these ones would be weak. Okay? But this one would have the greatest strength. The greatest acid strength. Okay. So, now we're going to look at how salts can be either acidic or basic, depending on the salt that you're using. So salts are ionic compounds, right? And Salts containing alkali metals or earth metals, except for Be, will be neutral, right? So, for example, sodium chloride. Sodium and chlorine. Chlorine is not a strong conjugate base of HCl. So if I ask what is the conjugate acid of Cl minus, it would be HCl. But Cl minus is not a strong enough base to actually go backwards and create HCl in solution. So if I dissolve sodium chloride, my solution doesn't become acidic or basic. It doesn't become basic because chlorine is not going to create any equilibriums with HCl. Okay? So these will be neutral. Salts derived from a strong base and a weak acid will give you a basic solution. Okay? So something like sodium hydroxide would be a strong base. Okay? And that would obviously be basic because you're going to produce hydroxides. Sodium hydroxide would dissociate. But this is also a salt derived from a weak acid. It's the conjugate base of a weak acid. What weak acid? What the heck? Oh, okay, I see what they did. These people. That's not supposed to be there. There we go. That's better. Okay? So we have this ion right here, which is acetate. And acetate on sodium would produce sodium acetate. And sodium acetate, if you dissolve it in solution, will give you sodium and acetate ion in solution. And then once you dissolve that in solution, the sodium does nothing because it's just a spectator. But the acetate is a base. So it would create an in solution equilibrium with its conjugate acid. Acetic acid and produce OH minus in solution. So if I dissolve sodium acetate into water, this is what it does. It dissociates first like this, 100%. And then all those CH3, COO minuses will start to pull hydrogens off of water in solution and create acetic acid and hydroxide in solution. Okay? And they will create that equilibrium step. So this would be able to establish a pH of the solution. It would be a basic pH because it would produce hydroxide. Okay? So I could ask you, if you have a 0.318 molar solution of sodium acetate, what is the pH? Well, this 0.318 molar solution dissociates into 0.318 molar sodium and 0.318 molar acetate, and so that's where you would start. 0.318 molar here. This would be 0, this would be 0, and I could find the OH minus, right? And you would be able to tell me what is the pH of that. You would find the POH and then find the pH. Okay? So that's kind of the idea for these salts of basic, from the conjugate bases of weak acids, okay? For these salts of the bases. Oh, gosh. Okay, so here, once again, you can see that. All right? Yes. Okay, so acidic solutions. Salt derived from strong acid, obviously HCl would be like a strong acid. It's going to dissociate 100%. Or or from a weak base. So ammonia, if I asked you what is the conjugate acid of ammonia, you would say ammonium, NH4. Positive. It's an ion. So I can actually deliver NH4 positive to solution if I slap a chlorine onto it. Ammonium chloride. Now I dissolve that ammonium chloride in solution and it produces this, NH4 plus and Cl minus. The Cl minus we know doesn't do anything. It is not a strong base, or it's not a weak base. It's not nothing base, okay? So it just doesn't do anything. The NH4 though is a weak acid. So NH4 positive will set up an equilibrium with H plus plus and H3 in solution. So if my ammonium chloride concentration was 0.018 molar, then these would all be 0.018 molar, 0.018 molar. Chlorine doesn't do anything, but this would start out at 0.018 molar. These would be at 0. And then I could solve for H plus, right? And I can determine the pH of that solution.
So we're going to have to know how to break it up just like that.
You need to be able to recognize that. Okay? Because you will have questions sometimes where it says you have a 0.018 molar ammonium chloride solution. What's the pH of it? Okay? And they'll give you a Ka. Or they'll give you a Kb. You got to convert it to the Ka, and you'll be able to find the pH. Okay? Which part of it? This top part? Right here? This part. Okay, so NH4 plus is the conjugate acid of NH3, right? What's that? Conjugates are, okay. Let me do this. Let's practice conjugates a little bit. Okay. So, practice everything. Yeah. Nope, it's minus. I have an eraser. Just forget that. Okay, what is the conjugate? What is the conjugate base of H2PO4 minus? So if I'm asking you what the base is, the conjugate base, that means this is a what?
Acid.
This is an acid. So what is its conjugate base? What is the definition of an acid? Okay, so what's the conjugate base?
H3PO4.
HPO4. Yes. The conjugate base of H2PO4 is HPO4 2 minus because it lost one hydrogen. What is the conjugate base of HPO4 2 minus? Phosphate. Yeah. What is the conjugate acid of H2PO4? Yeah.
Is HPO4, is that a base?
Is HPO4 a base?
Yeah, because you brought it down, you took out.
It's the conjugate base of H2PO4 minus.
So that's
But
the
it's still an
conjugate base,
acid?
and then you're getting the conjugate acid now?
So let me do
That's
this.
the confusing part, because HPO4 is still an acid, right?
Yeah.
It's like a
But it's less.
conjugate base
Of
H2.
H2PO4.
That's the confusing part.
So
Okay.
what happens is from there, when you go and you add more hydrogen, you're actually becoming more acidic.
That's true.
So
Yes.
that's why it's the conjugate acid.
Uh-huh.
You go down from there, you become
Ka.
more basic.
The
So by taking
Ka.
away the hydrogens, you become more and more
Right, right,
basic.
right. But it's still, we're seeing this and it's saying, what's HPO4, hydrophosphoric acid, whatever it is. We're seeing acid, but then you keep calling it the conjugate base. So now it's, that clears it up a little bit. It's just the conjugate base of the thing with one more
That's right.
hydrogen on it.
What is the conjugate acid of HPO4 2 minus?
H2PO4.
H2PO4 minus. Because if I ask for the conjugate acid, that means this is a base. It's acting as a base. Okay? You can react, and you'll see this in organic chemistry a lot. You can react an acid with an acid, and one of them will act as a base because one of them is going to be stronger than the other. The thing that is the stronger acid is going to act as the acid, and it's going to grab hydrogens from the thing that would normally be an acid but donates hydrogens because its acid strength is not as strong. Okay. Like water. Water can act as both an acid and a base, right?
Well, we don't really necessarily consider it an acid, but it could be, according to.
Well, okay, so in this case, if we, let me see here. What's going on? Okay.
So is H2O a conjugate base for H3O? Is that like? Is that what he means?
Okay, so if I take NH3, oh, I changed my color, plus OH, plus H2O, okay? In this case, water is acting as an acid because ammonia is a stronger base than water. So it becomes NH4 positive plus OH minus. But in the case of something that is an acid and you're reacting it with water, okay, so something that like CH3COOH plus H2O, acetic acid is a stronger acid than water. And so it creates in solution H3O plus OH minus. Okay? This here is the acid, this here is the base.
So it all depends on what you're reacting with.
Absolutely.
Okay.
Okay? That's what it matters. Okay. Okay, so in this case, we're not showing it reacting with the water, but if it was, we'd say H3O plus here and ammonium. We just leave the water off because we consider H plus and H3O plus to be the same thing. Okay? But the concept is this, that if I'm given a solution of NH4Cl, ammonium chloride, at a concentration of 0.018 molar, okay, and I dissolve it in solution, I should recognize that ammonium is an acid because it's the conjugate acid of NH3, which is a base. So if that's the case, then it's going to do this. And I should realize that my initial concentration here is 0.018. This is 0, and this is 0. Okay? And then I can solve.
Can you keep going with the NH3?
What do you mean keep going with the NH3?
Like NH3 and the NH2 and H plus?
No.
We just need to know.
You could, but it's not going to really happen. Okay? You could create NH2 negative, but that's not really a step that because this is a base, it's really going to set up an equilibrium here. It doesn't really go to another step. It's too weak of a step that it doesn't really happen. But you might see NH2 minus, but you're not really going to see that. Okay. All right. So now salts with highly charged metal cations. Okay. So like Al3+, Cr3+, and Be2+, these cause the acid to increase in a solution where these ions are placed because they get surrounded by water molecules. Okay? And what happens is when those water molecules surround them, like in this situation here, okay, then by the oxygens here, then all of a sudden the chosen one of those water molecules is going to become acidic, and another water molecule interacting with it is going to pull hydrogen off and become H3O+. And now you have an acid solution. Okay? So you can see that the water surrounding the metal cation, it's highly charged. It's a highly charged metal cation, like Al3+, the chromium ion. Whoa. Okay? Oh. No. Okay, like the chromium and the beryllium, these are highly charged metals in solution, and they will create those 6 hydrogens surrounding it. And in the end, one of the waters is going to lose a hydrogen, create that H3O+ in solution. Okay, H3O+. Okay, and that's what it's going to essentially look like. Okay, so this might be answer some of your earlier questions. Okay, whoops, too far. Okay, so the Kb for an anion is greater than the K for the cation. The solution will be basic. So if you have the Ka and the Kb, so for example, we were talking about HPO4 2-. The Kb for HPO4 2-. Okay, we'll look that up. Look it up. Under our polyprotic acids. Okay. The Kb for that is equal to 1.6 times 10 to the negative 7. Whereas the Ka for this same thing, the Ka for it is 4.8 times 10 to the negative 13. So if your Kb is greater than your Ka, the solution will be basic. Okay? Because this is telling me the strength of this. This is a stronger base than it is an acid. So it's not going to act like an acid, it's going to act like a base. Okay? If the Kb is less than the Ka, the solution will be acidic. So let's take an example here. H2 PO4 minus. Kb for H2 PO4 is 1.3 times 10 to the negative 12, and the Ka for H2 PO4 minus is 6.2 times 10 to the negative 8. So it's going to act as a what? As an acid, right? It's going to act as an acid instead of a base because so dihydrogen phosphate is going to act as
What's an example of a problem that we might see where they could be asking if a solution is more basic or acidic?
well, they would just say based on these this Ka and the Kb of this.
So they would give us the Ka and the Kb?
Oh yeah, those are always given. Those you can even look them up. Okay, so if they didn't give it to you, just come look it up in a chart and find and look at what they are, okay, so that you could determine what it would be. Okay. So here, if we have these types of solutions, then your pH is going to be approximately 7, right? Here is sodium acetate. So we have sodium acetate here and potassium nitrate. Potassium nitrite, okay? And those would both be basic salt solutions. So the sodium and the potassium would just come off. They're not important, okay? What we care about is that this is going to become H, or CH3COOH, and this is going to become HNO2 after I dissolve those. And because it creates that equilibrium, it's producing hydroxide. So CH3COO minus means that it's deficient in a hydrogen. It's missing something, okay? Plus H2O produces CH3COOH plus OH minus, or NO2 minus plus H2O produces HNO2 plus OH minus, okay? Because those guys are working as, they're acting as bases. So this is a good indication that you have a base, okay? If you're missing a hydrogen. It's a good indication that it's a...
So that step, so KNO2 go into K and NO2 minus.
That's
then
right.
NO2 minus will set up the equilibrium with water.
That's exactly right.
Yeah, HNO2.
Mm-hmm. And here they give us pretty much the same example here, which is kind of ridiculous, but ammonium chloride, ammonium nitrate. Both of those are delivering ammonium. So the chlorine and the nitrate, those are simply delivery molecules. They are delivering that NH4 into solution because it's an ion. So NH3 is not an ion. I can have that as a pure substance, right? NH3. But the NH4, to deliver it into solution, I need to, because it's an ion, I need to put it with something.
So it can be soluble?
So it can be soluble, so I can put it into solution, exactly. Okay? Whereas NH3, I could have a pure thing of ammonia because it's a stable compound. And H3, there's no charge on it. Okay? But if it's a charged ionic element, I need something to deliver that. So I put an anion or a cation that will become a spectator onto it so I can deliver it. Okay? So ammonium nitrate. Okay, so here we have two things working against each other, right? So NH4 and NO2. NH4 is going to react with water. This is positive, this is negative. Okay? And it is a weak acid, so it's going to create NH3 plus H3O plus, whereas this one is a weak base, so it's going to produce HNO2 plus OH minus. So then you get an acid and a base working against each other, and you see it could be neutral because you might produce, depending on the Kas and the Kbs and the concentrations, obviously. They would be at the same concentrations. So depending on what their Ka or their Kb is, whichever one's stronger would win out, okay, for either acidity or base. So if the Kb of NH4 was stronger than the Ka of NO2, if the Kb of NO2 minus was stronger than the Ka of NO4 plus, then this would become a basic solution. Okay? Let's see. Maybe I can look those up.
Like the NH4, NO3, isn't NO3 or NO2? Like how do we not I don't know, never mind.
Say it again. No, go ahead.
So we're looking at like KNO2 and KNO3.
KNO2.
So KNO3 is gonna, so KNO2, you said the K goes away, so KNO3 would be the same thing, right?
No, because KNO3, okay, good question. KNO3, NO3 nitrate is not a base. It's nothing. It's a spectator. So KNO3 would be more this situation. Right? In fact, there it is.
Right. But NO3, because you said
It doesn't.
NO2 and IO2, right? So it's
Yes, but NO3 is not a basic ion. NO3 is just a spectator ion. It does nothing. It just gets delivered and it just remains in solution, does nothing.
So we
Like
just need to know
chlorine,
that it's
like
a spectator.
Cl is a spectator ion. It gets delivered, does nothing because it doesn't have any basic properties.
So we just need to know that. Basically.
You need to know that about chlorine and nitrate and those sorts of things. They're simply delivery molecules. They deliver stuff. Okay?
There's no way to tell. You just gotta, you have to kind of.
Well, yeah, so for NO3, HNO3 is a strong acid, right?
Yes.
Okay? So it would produce NO3 in solution, and the reason is HNO3 is a strong acid is because NO3 does not create an equilibrium going back, right? So because it doesn't do that, you would know that NO3 is just a spectator. It doesn't go backwards. Okay? Just like chlorine, HCl. HCl is a strong acid. Produces H plus and CO minus. CO minus doesn't push back. So it's just a spectator. Okay, so NO2 here, 2.2 times 10 to the negative 11. H4. Okay, so which one's stronger? The acid or the base? Those are the Ka and the Kb's. This is the Ka. This is the Kb. So it would end up being more acidic, right? So if the Kb is less than the Ka, then you have a pH lower than 7. It's acidic. If your Kb is greater than your Ka, then you have it greater than 7, and it would be basic. Okay? So that's how these Kas help you identify what your solution is going to be doing, whether it's going basic or acidic. Okay? Okay, I think so this kind of just shows you, it gives you kind of a good view of how on the periodic table you could kind of identify acids and bases. You can see most of the acids are those nonmetals over there, and then once you get into these metals, you're going to become more of a basic ion. These would have both properties of acids and bases, more so. Okay, in there.
What's that? Ampho.
Yeah, meaning they would have both. Amphoteric oxides.
So they could either be an acid or a base.
They would have, well, essentially they would have, that's kind of that area, yeah, where they would be. So where they would be kind of in the middle between those. Kind of like the why can't I think of the word? The not the transition metals, but the we're not going to make it worse, but non-metals, metals, and metalloids. Thank you. Yeah, kind of in the metalloid area. Okay. All right. Okay. So if I take, well, let's go ahead and take a break. Take a break. Give you guys a minute to digest all that other stuff. 10 minutes. We'll give you 10 minutes.
So, Not that. Send it to you automatically, or do I have to?
You don't have to do anything. Yeah, I'll have it.
Because yesterday when I was like going through it, I accidentally hit share, and it said like it's shared with you, and it was incomplete.
Yeah, you don't have to do share. Okay. Let's do this. All right, I think we'll try a few practice problems before we get to the rest of this chapter, just so we can stay on top of. It'll probably take the rest of the class, I would imagine. Okay. All right, so here's a good one to start out with. Okay, so Ka for benzoic acid is 6.5 times 10 to the negative 5. Okay, what is the pH? Okay, of a 0.1 molar solution. So you have a 0.1 molar solution of benzoic acid. The Ka is 6.5 times 10 to the negative 5. What's the pH? I know what your first question is going to be.
What's the chemical
Uh-huh.
benzoic acid?
Does it matter?
No.
Doesn't matter. Does it matter if I know the chemical formula of benzoic acid?
No, because we're not reacting it.
Just do this. HA. Whoops. Always forget I have a right. HA goes to H plus A minus. That's all you need to know. This is an acid. It's a weak acid. This is the chemical formula, general chemical formula of any acid. Doesn't matter the chemical. It doesn't matter what the chemical formula of benzoic is. You can set it up like this. Okay?
H equals H plus.
Yeah, but this is Ka is 6.5.
And then what is our K?
What are my initial concentrations? Here we go. 0.1 here, and H plus? 0 and 0.
And then you set up a price.
Oh, so
There you go.
So you just use 0.1 x squared to. Wait, where's
0.1.
0.1?
X squared over 0.1 equals 6.5 times 10 to the negative 5. That's right.
Oh, okay. pH of 0.1. Oh.
Okay, solve for X. Tell me what H plus is, and then tell me what the pH is.
Because you're starting first, you don't have to take first.
School for the good guys.
It's a plus x and a minus x.
It's a minus X plus X plus X. Because anytime you have 0 over here, it means you're going to add to it. You're going to have to get rid of some of this to add to that. It's getting easier, right?
Well, it's easy because we just did it. 2 days from now, when I'm like, what do I do? How do I start? Starting.
Okay. That's possible.
When I lock up and I freeze, I'm just gonna start sweating. I'm just gonna run. Pee myself and run. It's insane.
That way you were going to get
You should probably get some friends.
Is it 11? Let me look it up. That's a good question. Is that what you're getting, Patrick? 11?
It wouldn't be an acid. No.
That's true. That can't be the answer.
Oh, wait, so then it's 2.
I got. What did you get? Did you? I got 1.6. I'm on. What did you get? You didn't bring your special kind.
Don't you use
You
log?
can drop the X.
You use the negative log.
Negative log. Okay. That's fine.
So I dropped the X.
Once you find X, so you.
Find x and then take the negative log of it.
Okay.
Yeah.
Take this.
40.
So it's 2.5?
I'm gonna check.
So if you do this, so you get your concentration, and it's more than 5%, then you have to do that. Oh, you know what? We can work it out. Just so it's not one.
2.6.
Sure is. It is 2.6.
Okay, that's fine. Okay, so pH equals 2.6. Okay, that's what you should be getting to. What was your x equal to?
0.0025.
Okay? And then you take the negative log of that and get 2.6 as your pH. Okay, good. So that was not too bad, right? Okay, let me throw a monkey wrench in it. pH. This is actually easier, but you kind of have to think about it a little more. pH of an acid is 6.2. What is the Ka of a 0.01 molar solution? What's that? I'm sorry. 10 to the x. 10 to the negative 6.2. So you got to put it in as a negative. Yeah.
Oh, so A is negative 6.2. Is that what you said?
The pH is 6.2. So if you want to find the H plus ion concentration, you have to go 10 to the negative 6.2, which is the anti-log.
Oh.
Which might be something you want to do for this. My recommendation, set up a rice table again. And start filling it in with your information. What am I trying to find?
KA.
I'm trying to find the Ka, and to do that I have to find what? Ka equals, I need to find the concentrations of everything at what? At equilibrium. I need to find those concentrations at equilibrium. Do I know what this is? Okay.
That's the same as H plus.
Which is the same as H plus. Did I find H plus?
Which is the anti-log of negative 6.2.
Okay. So what is it?
6.31 times 10 to the -7.
Okay. So that means that's that. This is that. And this is minus 6.3 times 10 to the -7. So 6.3 times 10 to the -7. 6.3 times 10 to the -7. 0.01 minus 6.3 times 10 to the -7 is what? 0.01. Okay. It simply just rounds back up. Okay. All right. So essentially it will, because that's so small, right? That's such a small number. You can round it back up to that. And so my Ka is going to equal 6.3 times 10 to the -7 squared on top, divided by 0.01. Okay? So what are you guys finding for your Ka?
3.98 times 10 to the -11. Sound good?
Is it good? Okay. Yeah. Same. Good. Okay, so you see how that works? You're just working backwards. The rice table helps me identify what everything is. I know what X is because it's the H plus ion concentration. I can find the H plus ion concentration from the pH. So if I know the pH, I can identify all these other parts. And then I can solve for my Ka. Yep. Okay. Okay, what am I going to do here? What's the first step? What am I going to do? How am I going to answer this question? Point 0046. Is that what you're asking?
Yeah.
No ideas?
So it's H plus over.
I need the initial concentration, which I have. These are all the initials, right? And I need what? The equilibrium concentration of
Solution. Or the acid.
H plus, right? I need the initial I need the equilibrium concentration. I need to know what H plus is at equilibrium, right? And I'm going to put that over the initial concentration. How am I going to find the equilibrium concentration of H plus? I have a Ka. Solve for X using a Rice table. You got it. You're going to do that 3 times, right? You're going to solve for X using the Rice table 3 times. X is your H plus ion concentration, and then you'll put it over the initial concentration and tell me what the percent ionization for each of those is.
Oh, so we're doing each.
So we'll have 3 10% ionization.
Yes, you're going to have 3 different percent ionizations, and then we'll compare them. I'm sorry? It is. HF is a weak acid. It has a Ka. That's how I know it's a weak acid. If it was a strong acid, it would have 100% ionization.
Do we have to do 3 separate Rice tables?
Yes. Or if you can just somehow put them all kind of into one. Once you do one Rice table, you'll see how it all works. Basically, it's going to be this. X squared over 0.6, X squared over 0.0046, and X squared over 0.00028. Okay? Equal to the Ka. Actually, that's a good point, because once you get into these lower concentrations, it becomes less and less likely that it would be 5%. And then you'd want to do the, especially on those ones down there, the quadratic equation might become more necessary for these smaller concentrations than it would for these higher concentrations.
And that's actually, so to figure out if we can do the shortcut, it's the percent ionization, right?
Yeah, I said, yes, you're absolutely right.
Okay.
But you are right. I mean, around here, you're going to end up probably needing the quadratic.
Is there a way of doing it without doing the Rice table?
The Rice table helps you visualize it. I mean, if you can work it out in your head, I know that it's going to be this because I practiced it, right? So because I'm practiced, I know that it'd be x squared over 0.6 minus x, but I can drop the x and set it equal, okay?
Yeah.
So in that way, I don't really need a Rice table, but the Rice table really helps you visualize what's happening, okay? So, yeah, but be careful about that. Okay, did anybody get one for the first one here? What was the percent ionization? 3 what? Okay. Okay. 3.43. They're getting about 3.5. That's close enough. Okay. What about for the next one? Did we get that one yet?
32.
And did you use the quadratic, right? Okay. Because did you do the percent ionization before you did the quadratic to check?
I did. It was pretty close to that. It was
Pretty
like
close to
39%.
39, so it was a little high. Okay. What about for the last one? This one will probably be more.
76.8.
76.8%. Okay. And did you do the percent?
79.
Oh, it was 79 too. Okay.
79. Can't remember exactly.
Okay.
Oh no, 72. 32%.
It was 72. It was lower. Okay.
So it's better just to do the quadratic.
It's not that it's necessary here on these two, because look at the percentage is so high that to find the actual number we need to find the quadratic. Okay, because the difference between what you would actually 36 and 32 is big enough that you want to find 32, or 76 and 72 is big enough that you want to find that. Okay. So those are my percent ionizations. Look at the trend here. As the concentration increases, what happens to the percent ionization? Well, this is increased. As the concentration decreases, the percent ionization is increasing. Okay. So the smaller and smaller concentration, the higher and higher the ionization. The percent ionization. Okay, now let's just do it. Let's try a couple of these for bases. Okay, so what is the pH of a 0.1 molar NH3 if the K What is the pH of a 0.1 molar ammonia if the Ka is 5.5 times 10 to the negative 10?
Oh. See, that's like. It's easy when you have a teacher with a husband. When you're on the test. Or just chalk that up as a misprint.
Am I going to use the same equation for this? Am I going to use HA dissociates into H plus and A minus? NH3 plus water gives you NH4 plus OH minus. Or A minus plus water gives you HA plus OH minus. Okay? Would be the general equation. So here, if we're going to write it for ammonia, NH3 plus H2O produces in equilibrium NH4, which is the conjugate acid of NH3, plus OH minus, because the water donates that hydrogen. Okay.
And is that part given, or
No.
do we have to write that out?
You need to write that out. This is for a base. So with the acid, I don't need to include the water in the equation, but for the base I do, so I can see where the OH is coming from. Okay. So this is the general equation for the base. A minus plus H2O gives you HA plus OH minus. Okay? So this equation would work every time too. That's the general equation, which is essentially the opposite of the acid one, right? So here I'm going from A minus to HA, and the acid one I was going from HA to A minus. Okay, you use the negative log once you find what? X, and then that gives you what? Does it give you the pH? Gives you what? It gives you a P something, not a pH, it gives you a P. POH. From? Exactly.
So, okay.
And that'll be your pH.
So I got a pH of 5.1. I have to subtract that from 14, right?
You got a POH of 5.1?
Oh, sorry, POH. I don't know. I don't know if it's just a pH or a pH. Okay, so I got that. That's
So the NH3 is a weak base, right?
Yes.
That's written KB instead of K.
Yeah. Okay, guys. So I'm going to have initial concentration of NH3 here is 0.1, right? And of HA it's 0, and OH minus it's 0, or and of NH4, okay? Minus X, plus X, plus X, okay? So I have my rice table. I want to solve for it. So is X squared minus X squared divided by 0.1 going to equal this?
No.
Why not?
Wait, what did you say?
Is X squared?
Oh no, you need to get to KB.
I need a KB. So if you're solving using the Ka, that's wrong. This is not an acid, it's a
Base.
base. How do I find my Kb?
Divide that.
KW.
1.1 1 times 10 negative 14 divided by 5.5 times 10 to the negative 10. And that will give me my Kb. What is the Kb?
1.8 times 10 to the negative 5.
1.8.
Yeah, that sounds right. 1.8 times 10 negative 5. That's what it should be.
Can you say how you get the KB again?
Okay? You take Kw divided by Kb, Ka, will equal the Kb. So Kw is 1 times 10 negative 14, divided by the Ka, which is 5.5 times 10 negative 10, and that will give me my Kb. 1.8 times 10 to the negative 5.
And KW is a constant.
Yes. 1 times 10 to the negative 14 is the Kw.
Wait. Do we need to do that?
Do what?
All that? Can't we just change 0.1 molar to POH and then figure pH for that?
No, it's a weak base. You need to do this. Equals x squared over 0.1.
Right.
You have to do that.
I mean, that's what I did, but.
Yeah, you need to. This is not a strong base. If it was a strong base, then we could take the negative log of 0.1 and find the OH minus, and that would be our, and then find the pH. But that's not the case here. It's because it's a weak, It'd be too easy. Not that it's too easy. It's just that it's not a strong base. If it was a strong base, then absolutely. If it was 0.1 molar sodium hydroxide, then we would just say it's 0.1 molar OH minus. But this is not a strong base. It's a weak base. So we do have to do the rice table. Exactly. Exactly. Because it's a base. Kb will tell me the OH minus, a Ka will tell me the H plus. For the POH. That's the POH. Yeah. For the POH, it should be around that. But what's the pH? There you go. Okay, so I would solve for x. I'd find x to be about 1.3 times 10 to the negative 3. My POH, the negative log of that would be 2.89. And then the pH would therefore be 11.1. If I subtract 14 from 2.89, I get 11.1 as my pH. All right, let's try one more. Okay. pH equals 0.30 molar. Oh no, I'm sorry. pH equals 10.66. The base, the weak base, the A minus concentration is 0.30 molar. What is the Kb? A minus plus H2O goes to HA, the acid, plus OH minus. 11.1 was the pH. Did you get that? Okay. Take the anti-log of the pH. That'll give you your what? Now I wouldn't do that yet. I would actually go to your POH. Go from pH to POH because that'll give you OH minus. Take the anti-log of the POH will give you the OH minus. That'll be more useful here.
concentration, right?
Say that again.
Ethanol gives you concentration, right?
Concentration of,
Whatever you
yeah.
did it. Okay.
Yeah, I know what you mean. You need everything.
Okay, so this is where you should be getting. That the OH minus has a concentration of 4.6 times 10 to the negative 4, which would mean the HA has that, which means that if I subtract that from 0.3, it gives me approximately 0.3. So I square it, divide by 0.3, and that's going to give me my KB. Equals 4.6 times 10 to the negative 4 squared divided by 0.3. Okay? That's going to equal my KB 7.1 times 10 to the negative 7. It's 1 times 10 to the negative 14.
That's always, right?
Always, yeah.
Always.
Always. Okay, that's it. That's all we got time for today, guys.
Oh, you run it.
Next class.